Safety has been an issue since early times. The need for safe design is even mentioned in the Bible. In more modern times, however, a few engineers began to recognize the need to prevent hazards early in the industrial era, when the machines they were designing and building began to kill people. James Watt warned about the dangers of high-pressure steam engines in the early 1800s. The Davy safety lamp, invented around the same time, helped decrease some of the danger of methane gas explosions in mines. In 1869, George Westinghouse developed a brake based on compressed air, which made railroad travel vastly safer for riders and crew. In 1868, the first patent was granted by the U.S. Patent Office for a machine safety device, an interlocking guard used in a machine for filling bottles with carbonated water. Other patents soon appeared for guards for printing presses, two-hand controls, and circular saws, and other woodworking machines. Near the end of the 19th century, engineers began to consider safety as well as functionality in their designs instead of simply trying to add it on in the form of guards. While the use of guards was prevalent then and still is in workplace safety, much more sophisticated engineering solutions have been found and are used in complex systems. Many of the dangers involved in workplace accidents were due to the increasing use of engineered devices in the workplace. So there was much overlap at this early time in the history of safety engineering and workplace safety. A divergence between the two fields occurred later, as you will see. One of the first organizations to study accidents was the Society for Prevention of Accidents in Factories, called the Mulhouse Society, so named because it was founded in the town of Mulhouse in Alsace-Lorraine, in the area bordering France and Germany. The Mulhouse Society held annual meetings to exchange ideas about safety improvements in factories and published an encyclopedia of techniques for injury prevention in 1889 and 1895. By the early part of the 20th century, a German engineering society was established for the prevention of accidents. At about the same time, the engineering technical literature started to acknowledge that safety should be built into a design. The first paper dealing with the safe design of machinery was presented to the American Society of Mechanical Engineers by John H. Cooper in 1891. It is an easy task to formulate a plan of accident-preventing devices after the harm is done, but the wiser engineer foresees the possible weakness, as well as the dangers ahead which are involved in his new enterprise, and at once embodies all the necessary means of safety in his original design. In 1899, John Calder published a book in England, The Prevention of Factory Accidents, that provided accident statistics and described safety devices in detail. The book emphasized the need for anticipating accidents and building in safety, and argued that legislation to compel manufacturers to provide safe products would probably not be necessary. Free market forces would provide a stronger incentive. Safeguarding by the user of some kind can in the long run be compelled by statute. But the author's experience is that in the case of the multitude of occupiers of small factories with no mechanical facilities or aptitude, nothing can take the place of good fencing fitted by the makers, and all accidents thereby prevented by being anticipated. Later moved to the United States and changed his mind. By 1911, he was calling for legislation to force manufacturers to provide safe products. Trade journals started to editorialize about the need for designers to eliminate hazards from machinery. We reiterate that the time to safeguard machinery is when it is on the drawing board, and designers should awaken fully to a sense of their responsibility in this respect. They should consider safety as of equal importance with operating efficiency. For if the machines unprotected are not safe to work, they are failures, no matter how efficient they may be as producers. The first American technical journal devoted solely to accident prevention, the Journal of Industrial Safety, began publication in 1911, and individual states began to hold safety conferences. The first American National Safety Congress, organized by the Association of Iron and Steel Electrical Engineers, was held in Milwaukee in 1912. In 1914, the first safety standards published in the United States, the Universal Safety Standards, were compiled under the direction of Carl Hansen. These standards require first defining hazards and then finding ways to eliminate them by design. This approach is the essence of safety engineering today. Notice how far back it goes. Engineers at this time started to study safety as an independent topic. A study examined the widely held conviction that safer machines with guards were inefficient and resulted in reduced production. The study, conducted by a group that included the major engineering societies at the time, involved employees of 20 industries and 60 product groups who had a combined exposure of over 50 billion hours. The final report confirmed the hypothesis that production increased as safety increased, lessons still to be learned by many people today. The study also explained the historical increase in accidents despite industrial safety efforts to reduce them. The increase was found to be related to the tremendous increase in the rate at which American industry was becoming mechanized. Mechanization affected safety in three ways. 1. It displaced the use of hand tools. 2. It increased the exposure of maintenance personnel to machine hazards. And 3. It allowed increased operating and material feed speeds. The primary conclusion of the study was that while there has been this recent increase in the hazard of industry per man hour, production per man hour has increased so much more rapidly that the hazard in terms of production has decreased. Up to this point in time, there are two things to note. 1. Workplace safety and product safety were related and intertwined, primarily because many of the new engineered devices were used in workplaces and were created to reduce workplace injuries. At the same time, however, designing safety into more generally used hazardous products, such as the steam engine that affected public safety and not just the workplace, was also a focus of study and engineering practices. 2. Post-accident investigation was a very small part of safety engineering in the past, and now much more concern was placed on identifying hazards and designing safety into products from the beginning of development. Around the 1930s, workplace and product system safety diverged and started to develop separately. On the workplace safety side, in 1929, H.W. Heinrich, who worked for an insurance company and thus had access to a large number of accident reports, published a study of 50,000 industrial accidents, concluding that for every serious injury that occurred in the workplace, there were 20 minor injuries and 300 near misses without reportable injury. He also suggested that thousands of unsafe acts were occurring as well. Although it is not clear how he got this information from the accident, hypothesis became known as Heinrich's pyramid or triangle, shown in figure. Heinrich's hypothesis about ratios between serious accidents and less serious incidents does not apply to complex systems and product safety, although that has not deterred many people from applying it anyway. In complex engineered systems, accidents may result, and often do, from very different things than incidents. That is, the causality might not be related. Even some in occupational safety today are starting to doubt the validity of Heinrich's triangle. Heinrich was also the first to propose a conceptual model of accident causation in industrial safety called the domino model, which focuses on human error as the cause of accidents. The domino model is described in chapter 5. Seizing on these arguments, opponents of mechanical, i.e. engineering, solutions to workplace safety began to direct attention away from unsafe machinery and toward unsafe user acts. Claims were made that accident-prone workers and carelessness were responsible for 85 to 90% of all industrial accidents. These arguments were based major injury 29, minor injury 300, no injury, figure Heinrich's triangle, on the fact that accident investigations concluded that workers were responsible for most accidents and that accidents were occurring despite the use of machine guards. These arguments ignored the facts, of course, that one, finding workers responsible for accidents was to the advantage of the companies conducting the investigations, as that made them not responsible for the worker deaths and injuries, and that two, many accidents such as slips and falls or injuries from falling objects or from lifting were not machine related and thus could not be prevented by any type of guarding. More recent data shows that humans are more likely to be blamed for accidents than are unsafe conditions, even when unsafe conditions make human error almost inevitable. A more important question than assigning blame or cause may be how to eliminate accidents in the future. As Hansen wrote in 1915, forgetfulness, for example, is not a crime deserving of capital punishment. It is one of the universal frailties of humanity. The problem is, therefore, to destroy as far as possible the interrelationship between safety and the universal shortcomings, which can be done by designing the safeguards on machines and equipment so that if a man's acts are essential to safety, it becomes mechanically necessary for him to perform this act before proceeding with his task. This design principle, technically called an interlock, is one of many today and is common to workplace and product safety. Safety design principles are described in more detail in Module 11. The Depression, followed by World War II, temporarily diverted attention away from designing safety as well as function into products. In the long run, however, World War II led to even greater safety efforts and the divergence of workplace safety and product system safety. Along with greatly increased war manufacturing, the greatest manufacturing effort of all time, came a tremendous increase in accident and injury rates. The rates were so bad that the Allies were actually in danger of losing the war because of them. More people were killed in industrial accidents than on the battlefield. As Ferry writes, not so well known is that for a while, accidents in the workplace were nearly negating the increased production. We were losing twice as many aircraft in training accidents as in combat worldwide. In nearly all theaters of operation, ground and air accidents were 3 times those of the combat losses. With the realization that accidents at home were hurting military efforts, an enormous safety and health program was initiated, and thousands of people were trained for industrial safety work. We learned from those efforts that most accidents could be prevented and began to take appropriate action. When the war ended, health and safety activities no longer had a high priority, and safety records worsened again. As normal times and prosperity returned, many businesses and industries learned that safety was good business, and the accident and injury rates declined again. This increase in safety efforts, however, was not universal. At the same time, World War II marked the era when extremely dangerous new technology started to be created, such as advanced weapon systems, nuclear power, and highly dangerous chemicals. Increases in the use of some products, such as commercial aircraft, also contributed to public and governmental concern about product system safety. It is at this point that workplace safety and product system safety completely diverge, and almost no interaction between them has existed since. Each of the industries creating the different types of products also developed their own approaches to ensuring safety based on technological, social, and cultural differences. The result is described later in this chapter. With this brief introduction to the history of safety completed, let's look at the state of workplace safety and then product system safety today.